is you have your air handling unit, your duct system, blowing air out down a duct. Terminal boxes are that last device before it goes into the room or goes into the conditioned space. In the old days, kind of before air conditioning was widespread, you had an air handling unit, you'd have a ductwork running down the hall, and there'd be a duct poked into each room with a little bitty grill that dumped a little bit of fresh air into that space. And then you had a cabinet unit here, a fin tube, some sort of heat source in the room that heated it. And you had this little bit of air that dumped into it. When they set it up originally, there was a hand volume damper on it. The balancer went around and set all those dampers so they got about equal flow into every one of them. And that was fine as long as you were just dumping a tiny bit of air into every room. There was nowhere near enough air in those coming out those ducts to cool the room. You were just providing a little ventilation. As you get up into a type of system, duct system that's going to actually cool and condition the room, now you need to control that air going in somehow. The first variety, or probably most simple, is a VAV or a CAV, for variable air volume or constant air volume. If you start with the constant air volume, basically it's just a sheet metal box with a damper and an actuator. The actuator modulates to maintain CFM coming out. There's a pitot tube on the inlet of that thing with some sort of a velocity control measuring it that will pick up that CFM reading and modulate that damper to dump air in. If it's constant volume, the engineer decides it needs 800 CFM into that room. Balancer sets it at 800 and it just stays there. If it's a variable air volume system that got popular when energy got expensive, then as the space temperature changes, you're going to vary that amount of CFM you got going in. So you'll have a minimum and maximum set point. Say you'll have 1,000 CFM maximum and maybe 300 minimum. As the room temp warms up above set point, that CFM set point will go up. You'll open up your damper, get more airflow in to cool the space down. Usually your air handler is dumping out like 55-degree air. So the more 55-degree air you introduce into the space, the more it cools it down, hopefully. Once the room cools down below set point, then the damper can start modulating back. Once we get too cold in the room, the damper will choke back, get down to somewhere between that minimum and maximum set point. Gets too cold in the room, we'll go all the way down to the minimum and sit there. And once you're down there, sometimes they will have a minimum of 0, where you go all the way closed. Not very often, because you usually want that fresh air, that ventilation in the room. So you'll go down to that minimum, like that 300 CFM, and just trickle a little bit of air in just to give them some ventilation. Obviously your fan back at your air handling unit is of some set size. It's a 10,000 CFM fan, and that's all you're going to get out of it. So you have that maximum CFM set point on there so that if every box in the system is wide open, we still get enough air to every room we want. You know, so the first 4 boxes on the run don't steal 90% of the air, and the poor suckers down on the end don't get anything. So you have a maximum that will just keep it proportioned so that everybody gets their share and nobody gets too much. The next variety that we end up with is they stick a reheat coil on the same thing. And so the damper part sequence stays exactly the same. When you get cold in the room, that CFM modulates down to minimum set point, and then the hot water valve starts opening up to warm it back up, reheat that air back up from the 55 that was coming out of the air handler to something warmer to hopefully warm the room back up. Once it gets warmed up again, the hot water valve can close, and then the cooling cycle can start again if need be. Pretty simple. You know, you've got a damper, a velocity sensor, you know, a hot water valve. There's not a lot of controls there really. The next variety is fan-powered boxes. There must be a really good fan-powered box salesman in Omaha, because you guys seem to see a lot more of them than we do. In Lincoln, we don't see a whole lot of them, but I've seen a lot of them up here for some reason. Is that true, Mickey? Do you have a...
You don't see anything but heat pumps anyway, so what's the difference? Now, boxes get used quite a bit because they exterior loads or exterior applications, either the floor or perimeter, and or if the customer has a issue about constant airflow or variable airflow because their employees complain because they can feel the airflow going up or down, so it's a way to mask the VAV benefits.
Okay. Fan boxes really is the VAV box, only stick a fan there. There's really 2 configurations of the series where primary air that comes from that air handler goes through our damper and then into the return of the fan, which blows it out into the register into the room. And there's another path for the air directly into the return of that fan. It's just sucking around the room into the fan blowing at the end. So in that sort of a situation, you have the fan blowing substantially more air than you're being programmed with. You can modulate the damper to bring in as much cooling as you need to cool the room. Like make that you're going to have constant flow air all the time. The other configurations of those, they also stick a reheat coil on the end of it. Exact same thing as a normal VAV box. You bring it on when needed and shut it down when you don't. The other configuration is parallel. That was something really weird. The fan sucks air out of the room and blows into discharge, and the primary air from the air handler blows into that same discharge, and the next unit dumps into the room. And then you can also have the heat those. Now, in power boxes, you have ups and downs. If you want constant airflow, that's one way of doing it.
Only materials.
Yes, you're right. All right, with the parallels, it'll go up and down depending on how much primary air you pump in.
Anybody else would just tell us what the depend one or the other. Just based on this, going to give you enough information.
The parallel box isn't about taking the turn air and you know anything that's more like recycling air. Don't burn so you don't have to run upward and then the heat or cool. You don't cool it.
They both take turn air. So that's something they both do. What I'm writing at is the parallel box is a energy efficient system of 10 hour, only because the parallel only comes on in the heat mode. The series box, the fan lose, it runs constantly. It actually runs up against the edge of intercodes that if they allow them to do. They don't like it because they're intertone, frankly, because there's no fan in there all the time. But it improves the comfort zone, both psychologically and temperature-wise within the space, just because you keep constant airflow going within the space. It's not well constantly because you put the back this month, you a little fan room all the way.
Yeah, and really that is one of the big disadvantages of fan box. You got a plug box. There's not a lot to maintain. You know, like, everything you go over that a whole lot. Fan box. Now you've got a fan up there, and granted it's pretty small, horsepower-wise, but it's the fan motor with something you probably got to lubricate. You know, there's a blower wheel. There's a filter. You should be changing every month, right? Like that's ever happened on all those fan-powered boxes. But they take maintenance, and that fan makes noise. So, yeah, Fred?
Metrotech used a lot of them. They're big collections. They keep a constant flow. The students can't hear the changes. They get air movement keeps everybody awake,
Yeah,
and it works out real well for them.
yeah. Well, and that constant air movement that is really important. If air's blowing on you, even if it's the same temperature air, you feel cooler. You know, because your body's a lot warmer than even if it's 75-degree air, your body's a lot warmer than that, so that airflow makes you feel cooler, which is good when you want to feel cooler. And in the winter, on days like this when you're trying to get heat, you get complaints about that same airflow. But most of the time we're worried about cooling, you know, the space more than heating it. And so that airflow is usually a good thing. VAVs, you definitely, the noise level between a minimum and maximum set point can be really pronounced. You can really hear that air screaming through the registers, depending on what type of diffusers they used and how close, I mean, how much they're trying to dump out of every one. Did you?
Well, I don't know, are you gonna talk about control scheme for a series as opposed to a parallel?
Not really. Go ahead. Would you jump in? That's
well, I just
what
want
I have not worked with much.
I just want to inject something. Joe, I know, has been beaten up with the 2x4, proverbial 2x4 enough times, you know, with especially series powered fan power boxes, but all of you guys, especially the programmers, but even the installers, because when the programmer's out there telling you it's programmed and you're watching something operate, you need to know what's supposed to happen. On a series powered box, when you go to the initial startup of the air handling unit, you absolutely must turn on all the fan powered boxes first, right, Joe? Before the air handling unit comes up the line. Because if you don't, usually they have little fractional horsepower 120 volt motors in them. You will spin them backwards. With the primary air from the main air handling unit, you will burn up the motors. We've burned up, I don't know, a dozen, 2 dozen of them before we discovered this. The business park, Joe? It was in somewhere in that arena.
Yeah, so there was a lot of them.
I mean, before we all kind of discovered what the heck was going on. So, and you get into a series, for rule number 1 or step number 1, when you want to bring the air handler on us, give them all a kickstart. Give them a minute to 5 minute head start, you know, to get all the fans on, get them running in the right direction, you know, on their own, and then bring on the primary fan and bring it up to speed. Otherwise, we'll all be around here trying to buy new motors for fan power boxes because we did the control scheme incorrectly.
And there's generally nobody that knows that. I mean, the engineer won't tell you that.
No. Fan power box guy will tell you that after he's gone through a dozen motors,
Yeah,
saying something's wrong.
yeah,
And then
Oh, yeah.
Then they look for the guilty party.
yeah. And those things can, you get them spinning backwards and they start.
They'll stay going.
I've seen them stay going.
They will. They will go backwards on
They will
120
run
volts.
backwards. And they will keep going. And you get no air out of them, or almost nothing, but that motor will sit there and run backwards.
And it'll burn up at 120 volts. It tears them up.
So it is bad for them. That I meant to bring that up.
Sorry, Dan.
No, thank you. I'm not a huge fan of fan powered boxes, just for the reason of I hate having, you know how they always are, it's that box, if it was in this room, would be right over the top of this soffit with the panel you need to get to on the back side. And, you know, you got to deal with the inhabitants in the room, the noise, the maintenance. It's a lot of cost. Electrician has to run power around to it. At least with a VAV, you know, the fitter had to get hot water there and the duct was already there. But it's a little simpler. There's less to go wrong. Type is a mixing box. And those are used when you have a 2-duct system. You have a cold duct. So your air handler will have 2 big ducts coming off of it. One of them downstream of the cooling coil and the other one downstream of the heating coil. And the hot deck, you'll run anywhere from, you know, return temp up to maybe 140 degrees on the coldest day. Cold deck, you know, usually run at mixed air temperature, you know, 55 degrees or, you know, cooling whatever you can get off of your chilled water coil. So you got this hot air and you this chilled air stream, and they duct it out all through the building. And at the terminal, at the end, at the room, you'll have a mixing box that is just a box with 2 inlets and 1 outlet. One side's for the chill, the cold air, and the other side's for the hot air. And as that, they are generally constant volume. So you'll have a set point of whatever, 1,000 CFM, and whether you're getting it from the hot side or the cold side, that's what you get. That you're going to keep that 1,000 CFM constant all the time. Yes,
How
sir.
many diffusers can you have on these units?
As many as you need.
Doesn't matter.
No. No, they can be as small as, you know, one little bitty one, or I've seen them that were way too big for like a ballroom or something that, you know, were thousands of CFM. Usually they keep them below, I don't know, a few thousand, 2, 3.
Typically, a diffuser runs between
Wow.
150 CFM and I'm going to say on average 400 CFM. There's a lot of them don't, I mean, you guys program or see a lot of this, but isn't it like around 300, 350, 400 you see on a diffuser? Somewhere in that range. But then you can have, then you count how many CFM are coming out of that box, divide that by whatever that rough magical number is, and that tells you how many diffusers you end up usually trying to disperse within the area.
Right. Right, and actually, when we get done here, I kind of want to go into some of the problems that introduces for VAV systems.
May I ask a question?
Uh-huh.
Do you typically run the hot deck to 140 degrees?
You generally don't ever need to, but it depends on the building.
Okay.
If you have lots of outside wall and you're actually heating a lot, then you might need it pretty hot. But generally, no. So the mixing box, you're gonna mix these 2 air streams, dump it into the room, and that's it. Those 2 dampers are sort of like a mixed air in that they will, as the hot opens up to warm the room up, the cold is going to see that increase in CFM and close down so that we maintain that constant CFM. Those were real popular, dual duct for a while, probably not a real long time, but they kind of went away.
Like St. Joe Hospital was old pneumatics, and they had the same system there. With the stator system, and now we run these boxes where we just run a certain minimum, say 200 CFM on each hot and cold. And then when you want heat, the heat opens and the cold goes down. We can program how much air we want. Maybe 300 up to maybe 3,000 CFM. And there's 16-inch boxes up there with
Yeah.
3,000 CFM.
Pretty good size.
Yeah.
So you operate them like a dual VAV?
Yeah, basically. We got one hot, one cold.
But both can be down at minimum,
Oh,
rather
yeah.
than
You can program to do anything you want, really, so.
if
You
you
can
if you've
program,
got.
yeah, you can program it to operate like a constant volume. When one goes up, the other goes down. Okay? Or you can program like they do down there where, let's say a room like this, you'll put a minimum of 300, 150 hot, 150 cold. Then when you want heat, the heat starts coming on and the cold goes down to 0. And then when it reaches temperature, it just balances out. But it works pretty good.
Yeah.
You do have a change in pitch, and one of the problems they try to do is put one fuse because it's cheaper, and you have 1200 CFM roaring through there. So the answer is put a lot of diffusers, keeps the noise levels down.
Fred, what you're doing there at St. Joe is an ECM project, I mean, an energy conservation measure,
Yeah.
you know, modification. Original design, what Dan was talking about, it was meant to be a constant volume system.
Well, the
Where
old
you're
boxes
mixing-
are.
Huh?
There's a shaft, one shaft goes through. When one opens, the other one closes.
Right.
But
But,
we've since
yeah, modified them
modified those, yeah.
and created an ECM out of it in order to extract as much energy,
Right.
you know, or save as much energy as you possibly can. I mean,
Yeah.
it's a mutation, a variation of the general theme, which is a good way to go, Fred. That's not what I'm saying. It's just
No.
general, first initial design was to have it as a constant volume system. It's just they were energy hogs.
Yeah,
Yeah.
because your air handler back there is
Constant volume.
pumping out 10,000 CFM, even though the rooms only really they could get by with half that, you know, on a given day.
You send in the cool air that you reheat it up and vice versa.
Yeah, exactly. Every cubic foot of air costs money. You know, you gotta filter it, humidify it, dehumidify it, cool it, heat it, and get it out to the building. Get it out to where you want it. And every one of those steps costs you money at the moment. So with a mixing box set up or in the constant volumes, your costs are fixed because you're going to spend all that money to do all those things all the time. If you have a VAV system on a day when it's 95 out and you have to have full airflow everywhere, you know, on a design day to meet the load, then you're dumping that air out there and you're using it all on a 58 degree day. You have very little load, heating or cooling, and so you could get by with, maybe a third or a quarter of what that design CFM is. So in the old days, you used to put vortex dampers on the inlet fans, and plastic dampers, if you have never seen those, and it choked the air off to the fan, which allowed the fan to freewheel a bit, and so the amps went down a little bit. And it also reduced the amount of CFM you were blowing out in the duct. So when all these VAV boxes don't need all the air and they all back off, now your duct pressure goes up. And so you have to slow that down somehow. So you have to have some kind of fan control. Whether they be, the old days we did vortex dampers, which is basically just choking the air off and let the fan freewheel a little bit. Or nowadays we use VFDs, variable frequency drives, which actually reduce the amount of amperage that the motor is using, and slowing the RPM of the motor down. Yes, for that reason, because you cut down you had that big motor in the air handling unit, and the associated heating and cooling coils, whatever type you're using. If you can blow half the air, that's going to get a lot cheaper utility-wise than blowing 100%.
So I mean, of all the models, maybe the best of all.
Well, that is
Waiting for the answer here.
yeah. That depends on the application, really. It's one of the cheaper, energy-wise, because you are trying to limit all the utilities that you can. There's some, we're going to just get into some real inherent flaws in the VAV system that are, for us control people, kill us every day out there. They just make people Lincoln go away here. Sorry.
Yeah, I'm still there.
Basically all of these things have when I put a picture out on here, they all have a velocity sensor, generally on the inlet of the top. That mixing box, sometimes they'll have a velocity sensor on the hot deck and the cold deck. Sometimes they'll just have it on one of them and the discharge. Usually the cold deck and the discharge. Or no, usually the hot deck. I'm confused, I don't remember.
I worked at Northwest High in Bryan, and they had mixing boxes, and it was on cold deck
The cold deck?
and discharge.
Who
Because they
else
measured,
to do that?
they measured the total CFM and from the discharge, and that way, and in the wintertime, you need heat, so it already knew
Yeah, the heat would blow to
whatever it was set.
whatever it needed. Oh, you're saying that
The heating side was controlled by temperature, the cold deck side was controlled by velocity, by CFM, and the discharge, it's Kevin, right?
Yes, total CFM.
Yeah, total
Yeah.
CFM was telling the cooling CFM what it needed to do based on what the heating was told to do by the thermostat in order to maintain total.
right?
That was the
Yeah.
menage a trois that
So
was going on
you,
there.
you always knew your total CFM, and you could control your dampers
And
accordingly.
it seemed like the hot decks on both those pools were 25 to 30% bigger than the, there's 20 more volume of air coming down than the cold decks. If you had it fully closed off, it was,
Really?
yeah, it was bad because they couldn't balance it right. And they ended up lying to the hot deck saying it was smaller than it should have been, so you had to have a minimum of, so if you had 400 CFM come on, a minimum E of 40. You had to even lie to it about to drop down to 20. It was
I
took
didn't mean,
forever to figure out what was going on there.
because I've seen where the cold deck duct was considerably bigger than the
Over
hot
there,
deck.
they were hot.
Or if they burst their ducts open. Because usually they do it the other way.
There was a formula we threw up a few weeks back that explained that phenomenon. Does anybody remember what that formula is?
I don't.
BTU is equal to CFM times 1.08 times delta T, which delta T is the governing
Yeah.
factor between hot deck and cold deck. I mean, so that dictates size because of the amount of CFM. I mean, it all goes back to that stupid little formula.
Right. So like Mickey is saying, if this is my cross-section of my room, I've got this X number of cubic feet that is losing so many BTUs on a day like this. We got cold going out, or our heat is leaving the building, and we got to get back. We take 1.08 times the difference in temperature times cubic foot per minute and figure out how many BTUs we need to put back in. So the design engineer sits down and does these calculations on a degree heating and a degree cooling day and figures out how many CFM that is in order to get that kind of volume. Depending on our heat source, we can usually get a lot hotter than room temperature, so that can be a smaller quantity because we have a greater temperature difference. But back at our velocity sensors, back in the mid-18th century, they tell me Henry Pico designed this sensor for measuring flow. And according to the book, he was actually looking for a way to measure flow in a river. And so this was a water thing. But all it is a tube with a hole pointed into the flow, and then little holes on the side of it that are perpendicular to the flow. So in a duct, where we're measuring air, we've got static pressure. And what is static pressure? Anybody tell me?
Let somebody else answer.
Static pressure is just the pressure on the side of the duct. It's not, you've got a duct here with air hurtling down it at, 1,500 foot per minute. All we're worried about, static pressure, is just how much force is applied this way. If you had your duct, supply duct, you poke a hole in it, how much pressure is coming out right there? That's the static pressure. And that's usually what will control that, like the VFD, to maintain duct pressure, that duct static pressure. This pitot tube the opening is pointed into the flow, so the pressure going in here is the total static. That is going to be the pressure of the air being forced into it because it's blowing right in, and the static pressure.
It's called velocity pressure.
The difference is called velocity pressure. When you subtract this pressure coming in from this static pressure, you get velocity pressure. So if you had 5 inches of static in your duct and your pressure here, your total static was 5.5, your velocity pressure, just the pressure that's the velocity component, is going to be a 1/2 inch. So that's what these pitot tubes are measuring, is what is the velocity pressure. So we've got this thing that it measures this velocity pressure. We bring it into our Andover, and then what do we do with it? What we've got to do is take velocity pressure and make it mean something to us. What we're normally concerned about is cubic foot per minute. As the engineer tells us, you give me 1,000 cubic foot per minute into the room and it'll be comfortable. That'll be enough to cool it. So the formula here is 4,005 times the square root of the velocity pressure in inches of water column. That's going to tell you how many foot per minute you have of air shooting down the duct. That'll give you foot per minute. Then if you multiply your foot per minute times your cubic foot, that's going to give you cubic foot per minute. So that's not terribly complicated, but we have some issues. What's that?
Why is 4,500 constant?
I don't know. That is just a constant. That was, I don't know where that comes from, or if it's just a phenomenon that is.
Some really smart guy?
Some really smart guy, or some really, guy with a bunch of tables and numbers kept adding until he figured out, gee, if you multiply each one of these times 4,005. So our velocity pressure, since we're taking the square root of it, we're going to be a curve, between our velocity pressure and our CFM is going to be a curve. It's not going to be a nice, at 0.1 it's 100 CFM, and at 0.2 it's 200. It's not going to be a nice linear relationship. As we got that square root in there, we're a curve, which is no problem for like the Andover recruiter. You punch the formula in, tell it what the duct size is, and we measure the velocity pressure, and boom, we can crank out CFM, and everybody's happy, kind of. I put a little example on the back, and this is one of the great drawbacks of our VAV system or our pitot tube. Say we have an 8-inch round VAV duct. We got a velocity pressure of 0.415 inches of water column. We got a little under a ½ inch of velocity pressure. What's the CFM? So I wrote it out there. We find our foot per minute by multiplying taking the square root of 0.415, which ends up to be 0.644, times our 4,005, and we get 2,580 foot per minute, which is humming along the duct at a pretty good clip, I might add. The area of an 8-inch round duct is 50.27 square inches, but we need square feet in our calculation. So we divide by 144, and that converts us to square foot, which is 0.349. So we take our foot per minute times our square foot, and we end up with 900 CFM. Pretty typical application and calculation that we would do on a VAV box, 8-inch box, 900 CFM coming out, probably pretty much wide open. No problem there. Okay, since this is a VAV system, the engineer's telling me I want the minimum CFM to be 300 CFM. Because if you pump 900 CFM into that room all the time, it's going to freeze them out. So we're going to have to back it off to 300 as our minimum. So at 300 CFM, what's our velocity pressure? Let's solve backwards and go through the math there, and I come up with 0.0465 inches or water column. So at 900, what did I say I had? I had 0.415. I have and at 300, I have 0.0465. Does anybody see a problem here? Anybody at all? What do you think, Mark?
It's not linear.
Now, it's not linear. What's going to happen here? This is, we do this every day. We tell our VAV box, back off to 300 CFM. You know, the one in this room, drop down. But
You make a lot of noise.
well, this could be, but let's say the 900, he's designing, you know, four registers. You know, we separate it out. We don't have a lot of airflow. Give you a hint here. The Andover has the onboard airflow sensor on the 850.
It's only accurate to 50 thousandths inches of water column.
It is a 0 to 1 inch sensor. 0 to 1. And when we're trying to measure 0.415, you know, we're 40% up into the, what did the office call it? You know, on a 0 to 1 scale, you know, and we're measuring right there, you know, we're off there in the middle and we're probably got real good accuracy. Now, when I get down to 300 CFM, I'm only trying to measure 0.04. You know, we're almost 0.05. So now on my scale here, I'm trying to measure. We're barely on the scale. We are so low. The resolution of, I think I wrote it down here. It's 0 to 1 inch range, and the resolution is 0.005, which is okay, but the accuracy is plus or minus 0.05. So the accuracy is plus or minus 0.05. I'm trying to read 0.04. So I'm even below what the accuracy of the sensor is, and I'm trying to do it almost at 0 at the bottom of the scale. In the old days of mechanical controls, like a pressure gauge with an old Borden tube in there that flexed as you put pressure on it, the most accurate place in the range, you know, is going to be out there in the middle. I mean, I've heard 2/3, you know, is the most accurate place, but it's out there in the middle. Electronic doesn't suffer from that same problem. You get a lot better accuracy through the whole range. But you're trying to measure that close to 0 to the bottom end of your scale, you're in huge trouble. So if this thing is jumping in, you know, .01 jumps, you know, even .008, that calculates out to be quite a few CFM. So has anybody sat there and watched on your continuum screen at the VAV box reading, look at the input, not the numeric. We'll have a CFM numeric. But don't look at that, look at the actual input. And what happens is the CFM will go down, you'll see 500, you'll see 400, you'll see 0. And the box says, oh crap, I gotta come back open again. And so the box will open up ever so slowly. And then, oh, we got 500, we got 400, we got 0. And it's gonna sit there and do that all day, forever. Because we cannot accurately read when we get down that low. So what we end up with is at the upper end, out in the middle somewhere, we've probably got pretty dang good accuracy. But way down, real low, we lose all of our accuracy. It's going to be really bad. We try and do it all the time. You know, realistically, we come down, the damper moves down a little bit, our reading drops to 0. Doesn't mean the flow drops to 0. We just can't read it anymore. We open it up a little bit, it comes back up on the scale, we read it a little more, we back off again. It's bouncing up and down. Nobody will probably ever notice, and it'll probably be fine. But we have a real accuracy problem, and we have another problem. Okay, it gets cold in the room. VAV box backs off to minimum. So we're here controlling at minimum, as low as we can. It's still cold in the room, so the reheat coil opens up. And now we've got 55-degree air coming from the air handler, goes through the reheat coil. It's got 150-degree water in it. We warm that air up to 120 degrees. We got nice toasty warm air coming out the diffusers. Okay, here's my cross section of the room. This is a normal 8-foot or so ceiling. We've got a couple of diffusers. Let's say we started with, for easy math, 1200 CFM is our design CFM, our high end. We got 1200. Let's say they decided they wanted to put 4 diffusers in the room. It's a room like this one. They put 4 diffusers in, so we're going to have 300 each. 300 times 4. Now they probably arrived at that saying to themselves, okay, when I have 300 CFM coming out of that register, I'm going to size that register so that I get throw of the register to get down near the occupants, but not necessarily blow their hair off, but get it down into the room. Now that's at 1200 CFM. But we don't have 1200 CFM. We've got 300, 400 CFM. Let's say our minimum is 400. We got 400 CFM coming out of 4 registers. Now if you stuck your hand up to that register and tried to feel 100 CFM, how do you think you'd do? You're going to feel hardly anything. It's going to be trickling out of there. So what does that do? When we had 300 coming out, we had some pretty good throw getting it down there. And of course it was cold air too, so throwing cold air down is a lot easier. It's like throwing with the wind. Now I've got hot air at 400 CFM or 100 CFM coming out of here, and here's what I get. It comes out of here, it trickles along the ceiling, and since all the other ductwork was up in the ceiling, let's put the return up there too. We'll have our return duct here. You know, there's our egg crate over in the corner. So all this air comes out, trickles over, and sucks up into the return. Here's the occupant of the building sitting on a chair down here. Joe is sitting there at, you guys are probably sitting, your head height is probably about 4 foot off the ground right now. This heat is never going to see you. It is never going to get anywhere close. The ceiling, on the other hand, the top 12 inches of the room is going to be 120 degrees. But down here at floor level, you get into a kindergarten room where they're already this far off the ground and they spend most of it sitting down. The floor is 50 degrees and it's 120 up there, and we can't get heat to where we need. So one of the things we can do is when we back off to minimum CFM, we open our valve up, we start blowing hot water in. If here at 48 inches, our temp sensor height, if we don't get heat down to that, because that's what we don't know what the ceiling temperature or the floor temperature is. All we know is what's right there at 48 inches. If we don't get heat down there, we can start ramping this back up, the CFM back up towards maximum to try and get air blowing back down. Rooms that are difficult to heat, if you've got a lot of windows, you're on a north face, you're going to have this all the time. And so you end up, you either got to raise your minimum up, or we'll often now program it such that we will raise the CFM back up to whatever in order to get throw out of the registers and get some heat down of them.
Program it based on the continuing fall in space temperature, do you program it based on time, or?
The temperature. If that temperature doesn't come up, then, so we'll kind of do one of these. As our temperature drops, our CFM will go down, get to where our minimum is. We'll start opening our valve up. We get our valve all the way open. If we're not warm, start raising that CFM back up. Get it back up to where we need to, where we can actually blow some heat down into the room. Vic?
What Dan is saying here is absolutely positively true. He needs, and I don't know if we've huh?
I'm glad you concur.
Oh, no, it is. The problem, the issue we have here is it needs to be carried one step further. In the ASHRAE book, most engineers don't even know this or realize it because they don't read the ASHRAE book any more than the rest of us do, but it's our Bible. The phenomena that Dan's talking about there is the exact same phenomena. This is a high supply, high return. But one thing I would disagree with Dan on, and it's basically a twist in this thing. What the issue is, your thermostat becomes an altimeter. I mean, all it's doing is taking that thermal plane, just like you're swimming in a lake. You know how your feet are cool sometimes and your upper body's warm, you feel those thermal planes that's going there? It's because the two temperatures aren't mixing from top to bottom. I mean, and Dan's explained it perfectly up there is what the whole problem is. But just like I call it like snow skiing, what's the thing you do that nobody naturally wants to do when you're snow skiing down a mountain? If anybody's snow skiing, in order to get in control, you have to lean down the mountain and get into the front of your boots. I mean, it doesn't seem natural, but that's what you've got to do to get control. To get in control here is you have to raise your CFM. Again, we go back to this stupid little formula that I keep beating you all up on. BTU is equals CFM times delta T times 1.08. you lower your delta T. Instead of increasing the temperature that you have coming out of your diffuser, you lower it. You get it to within 15 degrees of your set point. In other words, let's say your set point, and I'm going to use easy numbers here, okay? Let's say we want to maintain the room at 75 degrees. That means the maximum discharge air temperature coming out of that box should not exceed 90 degrees. And the reason for that is the lower the delta T, the easier the temperature coming out of that box, the phenomenon that Dan just talked about out of the diffuser, will want to mix because it's not hotter or a greater delta T than what the floor temperature is, and therefore it stays buoyant and goes back up into the return air, just like what Dan was talking about. So the lower the delta T between what's coming out of that diffuser and what's coming that's on the floor, basically, the better that room will mix, and you'll get a more homogeneous room temperature on the floor. Most people always talk about a cool heat coming out of a heat pump because they usually don't get real warm air coming out of them, but it's a more even mix in the room because of that, because there's not a greater delta T. So if you're trying to pump 140 degrees out of that diffuser, it's just going to turn around and go right back upstairs because it's going to say, screw this, I'm really buoyant. I have a lot of energy here. I'm going to just go back up the other way. And so the trick is to get that delta T between set point and coming out of the diffuser as close as you can to 15 degrees or less. And that'll give you a better mix. But go back to the formula. BTU is equal to CFM times 1.8 times delta T. If I lower my delta T, you do exactly what Dan says. You have to raise the CFM because the BTU number stays constant. Because you've got to put in, let's say, 1,000 BTUs at that particular time in life in order to warm up that room. So if you lower the delta T, you've got to increase the CFM in order to maintain the same BTUs. But you'll get a better mix down at our 4.5 foot level, and 3 foot level where bodies are, heads are, that type of thing. So that is a point where I always harp on engineers and owners. I like discharge air sensors in the throat of anything that has a reheat coil on it.
Yeah.
Because now you can control that temperature and hold it, because otherwise you don't know, you're guessing at that spot. But if you have a discharge air sensor, you can control it, watch it, and maintain that delta T, which will give you a better mix within the room, and your thermostat no longer becomes an altimeter, it becomes actually a temperature sensing device because you're getting a better mix in the room. There have been lawsuits and engineers have been cleaned up like you can't believe because they don't know that one particular little phenomenon because they keep putting more and more heat into it and the room gets worse and worse.
Yeah. I agree with what you're saying. The greater the temperature difference between the two streams of air, the harder it is going to be to mix them. The problem with this situation ever working is it's like rolling uphill. Every time you roll it up, it wants to roll it right back. It's sucking, the fan is pulling the air up, and you're trying to push the air down, and it's just going to want to come back up. So natural flow is going to be back up to the register, to the return grill. And if, like Mick was saying, if you have a great difference in temperature, you've about eliminated any possibility of it ever happening. If the closer they are in temperature, the better off you're going to be. But somewhere in the middle, you come down to a point where you get more velocity out of there. And when you have more velocity through that hot water coil, it's also cooler because we're not raising it as, we're not heating it as much. So, it's kind of a double benefit. We're about out of time here, but a couple things quick I wanted to touch on. If I tell this to Titus or whatever box manufacturer, what they're going to come back and they're going to say, oh no, not our boxes. We have a special pickup in the, here's my box here, in the inlet. They always have theirs in the inlet, which is usually about this far away from the damper. And then they go on to tell you in the instructions that we want 3 duct diameters in straight duct in front of that pitot tube. Because we need this, when I got my pitot tube here, I've got to get some straight air like the nice picture that I gave you in the handout here, we can have nice laminar flow. That thing can read and give us a pretty accurate reading. If this area is swirling around, when it goes by there, that differential pressure is going to be whacked and it's not going to be accurate. So we've all seen this installation, right? Trunks come down, they got flex, usually about 13 foot of it. It's pinched off right there at the opening because the light was right there, so they had to cram it in there to make it work. And you've got no straight duct. Here's our pitot tube is right here. Here's our damper is right behind it. You know, there's nothing straight about any air anywhere near there. So, you know, if we can get a little bit of straight air before that box, you've got half a chance of getting a decent reading. Now, the box manufacturers will tell you that we don't use a pitot tube. We use a special amplifying, insert your trade name here. But when you open it up and look at it, all you see is this plastic thing. If I'm looking at a cross section here, here's one tube and here's another tube. They're back to back. One of them has holes on one side going downstream. The other one has holes going upstream. That's doing a... So if I'm looking down the duct, you got this thing here and there's a bunch of holes along there. And along the back side, you have the exact same thing. And instead of reading static or the pressure against the side of the duct, what they're reading is this downstream pressure. So you've got your air's flowing along here, it goes along here, and this kind of creates a little vortex, a little low pressure area. So instead of the normal static pressure, you get something a little bit less because you're getting a little vortex off of that. So they're not saying, well, with our box, they call it the K factor. Our K factor is not 4005 like you're using. You know, ours is something else. And so instead of needing 0.05 or instead of having 0.04 to get 300, you know, they'll throw out things like ours is, you know, 1.7 times greater than that. It's really amplifying the crap out of that signal. Well, do your math. What's 1.7 times 0.0465? It's still nothing. You know, you double nothing and it's still nothing. So don't ever argue with a box salesman because he'll try and pull this on you, and it helps. It's probably better than nothing, but that's what it is. So crummy installation is going to be a problem for you. Troubleshooting, you're going to get up there and they're going to send you out and say, hey, this box isn't reading CFM. What's wrong with it? And you come up and you open the can and, you know, it's hard to see what electrons are going through that airflow sensor. So you don't know what the heck to do. So you pull the tubes off, put your magnehelic on. You know, you got a nice 0 to 5 inch magnehelic.
Yeah, really.
And the needle just barely quivers. Well, if all you got's minimum CFM, you got 0.0 something, that might be right. Try and get the box wide open so you get up to where you're reading something above 0.1. You know, in my experience, you get much below, it'll read below 0.1, but you get much below there and it kind of trails off pretty fast. Some of those sensors will get down to a velocity pressure of like, I want to say it's 0.017, and that's like the minimum they'll read. So if you have a big box, that may calculate out to be 500 CFM on a 2000 CFM box, it may say, it won't ever drop below, that level, even with the damper completely closed, because of the resolution, you can't get down there. What the heck was the other thing? Straight duct. Get the damper open, put your magnehelic on, so you have something to read. The other thing is, Andover uses a hot wire anemometer type of device for their airflow sensor. And what that is a orifice you've got your, you hook your plastic on here on each end, going off to the two tubes on your pitot here, and they have a tiny heater and a tiny temp sensor and a tiny temp sensor and an orifice in there, and they know the exact area of that orifice, and they know exactly how much heat that heater is putting out, and so they measure the difference in temperature and calculate how much air is passing over that heater. That is the way that thing works. So we actually have air flowing through that sensor, which means on the high side, we've got a filter to keep any of the lint and crud out of that orifice and out of that sensor, because otherwise, you know what the inside of the ducts look like. They just fill up with dirt over the years. So you got to have that filter in there. And the other thing is by the book, those tubes can't be more than just long. If it's 1/4 inch, I believe it says 18 inches, and if it's longer than that, they want you to use 3/8. Because if you have too long of a distance, you're trying to send .05, through a little tube 10 feet away, you lose a lot in your lines. So keep those lines as absolutely short as you can. They've got to be absolutely tight, because you can't afford to lose anything. There's a lot of these manufacturers that will come with the pitot coming off of them, and they'll have little plastic T's with a plug in the T, so that when the balancer comes along, he can take those plugs off and plug his meter in there and see what the differential is across it. I see those things crack or split, or the little rubber stopper, the little rubber plug in the T falls off or gets old and deteriorates and falls away. I just cut them out. I would just remove those suckers. Get rid of them now. We have enough trouble with CFM. We don't need any help. Also, the pitot on the inlet are often made of plastic. If you have opportunity to see them before the duct work goes on, doesn't hurt to look at them, because sometimes they're cracked. And if that thing's cracked, then now we don't have the correct in or out pressure, and that's going to hose up your reading. The balancer will come along and put his hood on there with this big expensive differential pressure sensor reading his flow hood, and he'll tell you that that is absolutely, 657 CFM. And without changing any air whatsoever, he'll come back 5 minutes later and tell you it's 100 CFM different. And nothing has changed in the system. Everything's been locked down in between. So reading airflow is a pretty inexact science. Because of all the turbulence and all of these issues, it's tough to measure in the first place. So if you could get within 5% of real, you'd be doing fantastic. But I should probably let you go. Any last comments or questions? Anything? Brett?
I'm only filters, you ever changing? You know?
Do they need it?
Yeah.
I'm never around on the tail end of that anymore, so. Do they get?
Most of them don't know they're taking
Huh? No. Thanks, Lincoln, guys. Good.